Okay, so we have already discussed about the noise in AM. So, we have almost finished whatever we wanted to do in AM, and we have given a brief introduction in the last class about FM. So, today what we will do, we will try to explore FM more. There were a few controversy around FM. So, initially people thought probably with FM there is a huge bandwidth advantage. So, they thought okay, probably FM will give us the smallest bandwidth that is possible, and it was the initiative of bandwidth means you know that DSB was there, then SSB came or QAM came. So, people were thinking of a more bandwidth efficient modulation scheme, and then people came up with FM and they thought okay, this is probably the most bandwidth efficient. I can actually vary my bandwidth as I wish, and I can make the bandwidth almost infinitesimally small. We will demonstrate that, okay, why people have thought that, but that was a mistake probably. So, initially FM became very popular that they can actually save bandwidth by this. Then finally, when people started doing FM, they could realize that probably that is also something we will prove, that FM has infinite bandwidth. Instead of means controlling the bandwidth to the extent that it will be almost 10 to 0, and we can make really multiplexing hugely efficient by putting so many FM carriers. People realize that one single FM is almost taking infinite bandwidth. So, immediately what happens, the fate of FM was very bleak. People could understand that probably this is not the modulation scheme that we should try for. And then the bandwidth problem was in a way solved. People could realize that okay, it is neither 0 or tending towards 0 and nor tending towards infinity, it is somewhere in between, and we will try to prove that part, because FM bandwidth has bothered people, researcher, demonstrator and implementer alike for long time. So, we will do that, that is one of the major thing. And then people thought okay, it is a bandwidth not bandwidth efficient scheme, and they could prove that it is much lesser efficient compared to DSB-SC. So, it was even worse than DSB-SC. Of course, it is not that worse that it takes infinite bandwidth, but it was worse than DSB-SC. People could realize that the boundary I can get is not 0 bandwidth. So, it will be at least DSB-SC, and it can be even more. So, immediately the idea of FM was having a very negative response from the entire research community and entire implementers. And then Armstrong, thanks to Armstrong actually FM became so popular. So, he started inquiring other thing, that okay, communication we generally try to see bandwidth and all those things, that is all fine, bandwidth efficient, whether it is energy efficient and all those things. But there is also another thing, that you put a signal for communication, and then there is noise, there are interference, there are all those impairments that we have discussed which comes from the channel non-linearity. Then he started understanding whether FM has a good response in terms of those things, and then he could realize that that is also something we will be proving, that FM has potentially very good response against all these impairments, channel non-linearity, interference, and then noise in particular. So, that is the point where FM started becoming again popular, but Armstrong had to really fight hard, but that was legal battle. Nobody was trying to accept his technique, and then he had to fight a very long legal battle, and then finally he committed suicide also because of that. Because that took a toll from him. But anyway, because of him probably and all his battle, FM became the winner, and then people could see that all the radio actually started becoming FM, because you might have also experienced, if you have heard about Vividha Bharati in earlier days, and then all FM channels, FM has much better clarity. So, that is because it is more prone to noise, interference, channel non-linearity and all those things. So, it always transmits data with much bigger clarity, it is easier to receive the data in its original form. So, all those things actually helped FM to become a much more popular broadcasting channel. So, what we will try to do, this is just a summary of what we are targeting in FM, but we will try to see all these points that we have discussed, that the bandwidth issue, then the channel nonlinearity, how FM is better in that aspect, all those other channel impairments like noise and interference. So, we will try to prove all those things, but before that the first task is how do we really realize FM and what is the basis or genesis of FM. So, let us try to see that part. So, we have already told that it all started with the parameters of a sinusoidal, right. It is all carrier modulation. So, we need to see what are the things we can modulate. So, we have said that a sinusoidal or cosinusoidal, it is defined by 3 parameter, right. So, one is the amplitude, the other one is the frequency, and other one is the phase. Okay. So, whenever you do amplitude modulation, that is something we have covered already. When you start doing modulating these 2 parameters, we will also prove that they are probably similar. So, if you start doing that modulation, probably that is when the angle modulation comes into picture. That means either the omega c will be linearly varying with respect to the message signal, or the theta that is there will be linearly varying with respect to the modulating signal, like the amplitude was earlier varying with respect to the modulating signal, right, if you just think about DSB-SC. So, this was the target. So, then people started thinking that is FM and A means PM, that phase modulation or frequency modulation, are they almost 2 similar things. So, for that we need to establish the relationship between phase and frequency. So, if we start varying frequency or phase, what we will see is overall this whole thing inside will be varying with respect to time. Okay. So, let us just call this as a overall phase, okay, which is like a cosinusoidal, what value it takes, the angular value that it takes inside. So, that is the phase, it is a cosinusoidal of that particular value. For a signal which is having this varying this parameter with respect to time, let us plot that. Okay. So, with respect to let us say time, we start plotting this. So, what will happen? This particular phase will, of course, we can see with respect to time it will increase, okay, because there is a function t, and there will be some variation because this omega c might vary with time, theta might vary with time. So, there will be some variation. So, let us say probably this particular part is right now not varying. Okay. So, let us say it is like this, omega c t plus some theta 0. Okay. So, entire variation is over here. So, we are trying to capture the FM part. Okay. So, because this omega c t, that is also a function of t, this whole thing will now become a random variation of this particular thing. Okay. So, therefore, if omega c also was constant, I could have expected something like this, a linear curve, because then the theta t would be omega c t plus theta 0, where theta 0 is a constant, omega c is a constant. If that is the case, then theta t must be a linear function of t. So, it should be like this, where it cuts at theta 0 and the slope is omega c, right. This is something what we know. Okay. Now, what will happen if omega c start varying with respect to time? Then there will be a phase response which will be something like this. Okay. So, let us concentrate just for the time being a particular time t1 and a particular time which is close enough, which is called t2. Okay. And we are trying to concentrate on this interval, that is this t between this t1 and t2. Okay. And what we also do, that separation, we call that delta t, that is t2 minus t1, we make it infinitesimally small. So, almost tending towards 0. If we just do that, then at a particular instant, let us say at t1, what will be the instantaneous frequency? Okay. So, that is something we are trying to evaluate. So, at that point, this must be the phase, let us say that is theta I. So, I can say that theta I at that instance should be At this point, if I see from T1 to T2, if this theta I does not vary too much, okay. So then between T1 to T2 for all these values of t, it must be remaining constant, okay. So that theta I can just write at that point whatever omega c I will be getting into t plus theta 0, suppose I can write this way. Then what will happen? This particular part, if I just put a tangent over here, that must be the linear curve. So if I just say this is that omega c, okay, because of that tangent whatever slope it will be creating, I say that is the means that is omega c, okay. So for this instant I can write that omega c into t plus theta 0 wherever that tangent will cut this particular part. I can write it this way, right. So or instead of writing this as omega c, I can write it as instantaneous frequency at that instance, okay. Similarly at every instance I can start putting tangent wherever it will cut, that will become my theta initial phase, and then accordingly this particular thing will be coming out, right. So what I can see over here immediately, that basically the instantaneous frequency is becoming the slope of the tangent I draw over that theta I curve. This is something very clear, almost like when you start talking about velocity and acceleration, okay. So if the velocity was not constant, then the acceleration was similarly defined, right. It is the rate of change of velocity, and if the velocity goes in any extent, then you start defining it with respect to the tangent. Now the tangent from the differential calculus, we know that that is the differentiation of this particular part. So immediately what we can say, this omega I, which is the instantaneous frequency, that must be the differentiation of the phase which is happening over there at time t, okay. So this relationship I can always write, okay, or I can write omega t must be d theta dt, okay. So a time varying relationship of omega I can get, which is a differentiation of the overall phase of the cosinusoidal, okay. So this is something I can write. Now from here I can get the definition of theta. We know that differentiation and integration are actually conjugate, okay. So immediately I can write theta as from minus infinity to t omega alpha d alpha. So this relationship also I can easily write, right. So these two relationships fundamentally comes from our understanding of frequency and phase, okay. So if I just take overall phase and then try to define what is frequency, then frequency immediately, that angular frequency immediately becomes the instantaneous differentiation at that particular point, okay. So knowing this relationship, let us try to see what will be happening if I try to modulate a signal, that angular things we wish to modulate, okay. So let us say I have a theta t, okay. So now this theta t I want to vary instantaneously with respect to the input message signal, right. So this is something I can do. So immediately what I can do, it must be having a constant part omega c t plus it should be a linear variation with respect to that. So I can put some k p m t, okay. So what I am doing, the overall phase that is being created, that has a constant angular, this one due to angular frequency, constant this, plus means a constant angular frequency due to that whatever phase is being created, plus there is a variation due to the message signal itself. So this I can call a phase modulation, because the overall phase, how we define phase, it should be omega c t plus a theta. Now I am varying that theta linearly with respect to this m t. So whichever way m t is varying, I have just a linear means coefficient constant, which is constant k p. I multiply with that, I get the phase, and that phase I will be inserting in the signal. So, therefore, if my theta t becomes like this, the phase modulated signal must look like A cos theta t, which is nothing but A cos omega c t, right. This is what happens, no problem in this. Now, what we will try to see that what happens in the frequency of this part. So, what do we know about frequency? So, frequency must be, if this is that phase theta t, my frequency must be d dt of this. So, that should be my omega t, right. So, if I differentiate this, that should be omega c plus k p, differentiation of that. Okay. So, the differentiation I represent with a dot. So, this becomes my frequency. Now, what was my idea of FM modulation? The idea was that the frequency must now vary linearly with respect to a particular signal, which is almost happening. As you can see over here, the frequency, instantaneous frequency, which has a constant term that you can forget, and this is where the m dot t is actually modulating the frequency. So, what I can say, if I do a phase modulation, that is nothing but also a frequency modulation, but in the phase modulation I modify the phase with respect to m t, whereas if I have a frequency modulator, similar phase modulation I can create if first I differentiate my signal and then do a FM. So, correspondingly what will be created, that should be my PM, right. So, phase modulation is nothing but I first do a frequency modulation, but when I do frequency modulation, I also remember that if I do the frequency modulation with respect to the differentiation of that particular signal, then automatically that depicts the phase modulation, right. So, this is what we are trying to do. So, therefore, I can say that suppose I have a frequency modulator and I want to generate a phase modulator. So, what do I do? I take my MT, first I pass it through a differentiator circuit, okay, and then give it to the FM. So, FM will modify the frequency accordingly, and that is nothing but this. Okay, if the frequency gets modulated like this, automatically the phase will be this. So, that becomes, this whole module becomes the PM, right. This is just by seeing the relationship between phase and frequency we could see that. Okay. Similarly, what we can write, suppose I do a FM modulation now. So, what will happen? My omega c t should be some constant frequency plus some kf, another constant, into mt, because now I wish to do frequency modulation. So, frequency must be linearly dependent with respect to the input signal, that is what is happening. If this is the frequency, then what should be the phase? Phase must be integration, we have already derived that, integration from minus infinity t omega c t or alpha d alpha, which is nothing but integration minus infinity to t omega c alpha plus k f m alpha d alpha. This happens to be just omega c into t. So, this is omega c into t, okay, and this is just k f comes out integration minus infinity to t m alpha d alpha, right. So, that is my phase. So, what I can do from omega c, so basically I need, suppose I have a phase modulator, now you can see it very clearly. I have a phase modulator. So, what I do? First I pass it through my message signal, pass it through an integrator circuit, okay. So, I will get this, and then I actually modulate the, means I do a phase modulation with that, I get actually the frequency modulation. So, suppose I have a phase modulator, then what do I do? The message signal I pass it through a integrator, then I put a phase modulation. Correspondingly, whatever I get, that must be a frequency modulator. So, from this relationship between phase and frequency, what we can see that these two are almost equivalent. If I have one modulator, I can always construct another modulator just by using a linear circuit in front of that, either a differentiator or a integrator. Okay. So, if I have a PM, I use a integrator to get FM. If I have a FM modulator, then I just use a differentiator circuit in front of that to get PM. Okay. So, this is something we will be able to always do, and that is why probably all our discussion I can just do it for one, the other one will follow automatically, because the modulation as well as demodulation, all these things you can do very similarly. Okay. So, with that, can we just give a unified representation? So, that is something we will just say. So, we call it a generalized So, this is just the most generalized FM or PM modulation that we can give, or any other angular modulation that we can give. So, we can see if I just write it in this expression. So, it is A cos omega c t plus integration from minus infinity to t m alpha h t minus alpha d alpha. I will just explain what I have just written. Okay. So, we are saying that this is probably the most generalized representation of either PM or FM or any other variety of angle modulation. Why is that? So, I will just give you two examples. Let us say H t is equals to K p delta t, then what happens to this? So, if I just take this as delta, and if I just integrate a function multiplied by a delta function, it will just return me back the function itself, right. So, immediately what I will get, if I put this will become A cos omega c t plus I will get K p m t, which is nothing but PM. So, that is the phase modulated signal, because the phase is now, that phase portion is now linearly modulated with respect to the message signal. If instead of that I start putting H t equal to K f u t, now let us see what will happen. So, then this phi generalized angle modulation t will have a form which is nothing but omega c t plus, now I multiply with u t or u t minus alpha. That means it is actually just remains as m alpha, okay, because that will be from t equals to alpha to infinity, this will be 1. Okay. So, wherever I take that m alpha, it will be 1 over there. So, it should be just m alpha, rest of the things will be vanished. So, if I just do this integration, this will just look like minus infinity to t, that K f should be over here, m alpha d alpha. Can you again identify this form? This is actually the FM form. Okay. So, the frequency modulation can be realized by realizing a different H t. So, it is just almost like this H t, you can already see it is just like a impulse response of a particular transfer function that I am putting in front of the modulator. Okay. So, that is what you are trying to do. So, you just maybe you are having a FM modulator where the phase modulation you are creating by that transfer function. Okay. So, whichever transfer function you choose, accordingly either PM or FM will be generated. Okay. And not only that, we can also see a plethora of other things which are generated, which we do not know, because you can now take H anything and this will be one version of angle modulation. Okay. So, this generalized representation just tells us that we do not have just one option or two option, that FM or PM. There are in between multiple other options. Any H we put will probably get one kind of angle modulation, okay, whichever way that is, but it will have one angle modulation, because it is just with respect to my input signal, it is just modulating the angle. Okay. So, it just depends on what kind of transfer function you are putting. So, we have given two examples, those two examples actually takes us to PM or FM, and that is why when we are talking this as generalized angle modulation, probably that is true, because we can even get multiple other angle modulation using just this particular formula. Okay. So, once this is being done, what we can now start talking about is the bandwidth of FM. Okay. So, this was something which has been which was bothering people over the year, as I have already told in the introduction part of this particular class, that FM was initially thought that it has means I can vary the bandwidth according to my wish. So, I can have even 0 bandwidth. Okay. So, that was the initial assumption. Then people started seeing probably no, that is not true, FM actually have infinite bandwidth. Okay. So, it went from one extreme to another extreme, and why that has happened, probably we will try to examine that portion. So, what we will try to do in the next class is try to see this, why people had so many different versions of FM bandwidth. So, this is something we will try to explore in a better way, that will lead us to actual bandwidth calculation, which is known as Cutson's formula. So, we will first go through all this jungle of different bandwidth proposition for FM, and then we will probably try to hit the right thing where the actual FM bandwidth is being evaluated. It is neither infinity nor 0, it is somewhere in between, and then people could realize, which I have already told, that it is initially people thought it is bandwidth efficient. So, it was not bandwidth efficient, then people started thinking it might have infinite bandwidth, then people could realize that it is at least as worse as DSB-SC, it is not better than that. So, if you have to consider FM, of course, it is not infinite, but it will be as worse as DSB-SC. You cannot have anything lesser than a DSB-SC. So, it cannot be any way bandwidth efficient compared to any other amplitude modulation schemes. So, whichever we have discussed from DSB-SC to QAM to VSB to SSB, it is not better than any of those things. So, that is something we will try to prove first, and then we will see the other benefit of FM. Okay. Thank you.